News like this always gets people looking up and thinking.
Imaged it. And so that's what's really exciting. We want to take a picture of them. We want to take a spectrum of them. We want to find out what their atmosphere looks like. Know how the Earth formed, how the solar system formed. This is a snapshot into that process. 2 billion years into the future, it might be in a very different place. It might be at a place where it could support life.
Imagine for a moment a distant sun, cool and crimson, hanging in the velvet blackness 40 light-years from Earth. Around it whirl 7 rocky worlds, each roughly the size of our own planet, each locked in a cosmic dance that has captured the imagination of scientists and dreamers alike. This is the TRAPPIST-1 system, one of the most tantalizing planetary discoveries of the past decade and a potential treasure trove in our search for other Earths. When astronomers first trained their telescopes on TRAPPIST-1, the news electrified the world. 7 planets, all rocky, all huddling close to a small, restless red dwarf star. Some orbiting so near that their years last mere days. Some lying within the so-called habitable zone, that precious region where temperatures might allow lakes and oceans to shimmer under alien skies. Could this be the place where life, as we know it, has taken hold beyond our solar system? The quest to answer that question has led to one of the most ambitious undertakings in modern astronomy, the deployment of the James Webb Space Telescope. A marvel of engineering and international cooperation, Webb was designed to peer deeper into the cosmos than any telescope before it, to tease out the secrets of exoplanets and their atmospheres with astonishing precision. Recently, scientists turned Webb's golden eye toward one world in particular, TRAPPIST-1d, the third planet from its host star. This is a planet that sits right on the edge of the habitable zone, a cosmic sweet spot where, in theory, conditions might be just right for liquid water to exist. If any of the TRAPPIST-1 planets harbored a breathable atmosphere, the odds seemed best with 1d. But what did Webb find as it watched TRAPPIST-1d drift across the face of its parent star? Astronomers used a technique called transmission spectroscopy. As the planet transits or passes in front of its star, a fraction of starlight filters through whatever atmosphere, if any, envelops the planet. Molecules in that air absorb specific wavelengths of light, leaving subtle fingerprints that can be detected even from across the vastness of space. The search was for telltale signs: water vapor, methane, carbon dioxide, sulfur dioxide, molecules that might hint at processes familiar from our own world, or perhaps from strange alien chemistries. But the universe, as ever, had its own story to tell. After painstakingly correcting for the quirks of the TRAPPIST-1 star itself, its sunspots, its flares, the flickering variability of its light, scientists found nothing. No clear signature of an atmosphere, no robust evidence for the gases that wrap Earth in its protective embrace. The data, stark and silent, ruled out thick, Neptune-like atmospheres and even a cloudless, early Earth-style blanket of air. This was strike 3 for the innermost planets of the TRAPPIST-1 system. Earlier observations of TRAPPIST-1b and 1c, both orbiting even closer to their star, had also come up empty. For 1b and 1c, this was hardly a surprise. Blasted by intense radiation, the likelihood of them retaining atmospheres was always slim. But for TRAPPIST-1d, hopes had soared. Its location made it a prime candidate for habitability, or at least for the kind of atmosphere that could protect life, or even support it. Yet, science is not about wishing for a certain answer. It is about interrogating the universe as it is. As Caroline Piolet-Goroyeb, lead author on the study, reflected, "There's a part of me that would have loved to see signs of air on TRAPPIST-1d. Science isn't about hoping for a yes, it's about finding what's real." So here we've learned that TRAPPIST-1d is not an Earth twin. But does this mean TRAPPIST-1d is just a barren rock drifting through the cold and emptiness? Not necessarily. there are still possibilities, complexities that keep the story alive. It could have a very thin Mars-like atmosphere, one so tenuous that even Webb's sensitivity can't quite catch its signature. Or perhaps, thick, high-altitude clouds, like the sulfuric acid veils of Venus, are masking the signals, hiding whatever weather may churn below from distant eyes. The challenge is compounded by the nature of red dwarfs themselves. These stars, known as M-type stars, are the most common in our galaxy. They burn cooler and dimmer than our Sun, but they make up the vast majority of stars in the Milky Way. That means if life is common elsewhere, it might well be found on planets bathed in the ruddy glow of a red dwarf. Yet red dwarfs are notoriously unruly, prone to powerful flares and sunspots that can strip planetary atmospheres away or make observations fiendishly difficult. Transmission spectroscopy, for all its power, has its limits in these environments. Stellar contamination, the changing brightness and surface features of the star, can mimic or mask the signals astronomers are seeking. Webb's observations have shown that to truly probe these worlds, new techniques are needed. That's why the search is evolving. Rather than relying solely on transmission spectroscopy, astronomers are preparing to use the so-called secondary eclipse technique. In this method, they watch as a planet moves behind its star, allowing them to compare the combined light from star and planet to that of the star alone. This approach can help sidestep some of the challenges posed by stellar variability and could reveal new details about the atmospheres, or lack thereof, on these distant worlds. Despite the disappointment with TRAPPIST-1d, the story of the TRAPPIST-1 system is far from over. 4 planets remain, E, F, G, and H, each orbiting a little farther from their volatile star, each holding their own secrets. Perhaps, shielded from the worst of the stellar flares by their greater distance, one of these worlds has managed to hang on to its air, its weather, its potential for life. For now, what Webb's observations have delivered is a milestone in scientific capability. For the first time, if there had been an Earth-like atmosphere on a temperate, rocky exoplanet, we could have found it. No previous telescope, no earlier study had ever reached this level of precision. The universe remains silent, but our ears have never been sharper, our gaze never more focused. For astronomers, the findings from Webb's observations of TRAPPIST-1d are both a revelation and a reminder of the challenges that come with exploring the cosmos. The lack of a detectable atmosphere on this Earth-sized world, so tantalizingly close to its star's habitable zone, may dampen some hopes, but it doesn't close the chapter on the search for life beyond our solar system. Instead, it marks an extraordinary leap in our ability to probe distant worlds, to pull secrets from the faintest signals of starlight. Let's take a closer look at what this means for the ongoing exploration of the TRAPPIST-1 system. Discovered just 8 years ago, this remarkable family of 7 rocky planets, each roughly the size of Earth, has offered scientists an unprecedented laboratory for understanding planetary formation, atmospheric evolution, and the critical question of habitability. TRAPPIST-1d, in particular, captured imaginations because it orbits within the inner edge of its star's theoretical habitable zone, where temperatures might, under the right conditions, allow liquid water to exist. The James Webb Space Telescope was tasked with searching for signs of air, specifically water vapor, methane, carbon dioxide, and other gases that could betray the presence of an atmosphere. Using the technique of transmission spectroscopy, Webb watched as TRAPPIST-1d passed in front of its parent star. During these transits, if an atmosphere were present, molecules would absorb certain wavelengths of starlight, leaving telltale fingerprints in the spectrum. But this search isn't as simple as it sounds. Red dwarf stars like TRAPPIST-1 are notorious for their magnetic tempers, producing star spots and flares that can mask or mimic the signals astronomers are looking for. By painstakingly correcting for this stellar contamination, the research team was able to rule out thick, hydrogen-rich atmospheres and cloud-free envelopes similar to early Earth. Yet the absence of clear signatures doesn't mean the story is over. There remains the possibility of a thin, elusive atmosphere like Mars, or a world shrouded in high-altitude clouds, much like Venus. Each scenario presents new questions, demanding further observations and more refined techniques. Crucially, this is where the scientific process shines. Each discovery, even those that seem disappointing at first, carves away the vast unknown, leaving us with a clearer map of what's possible. As lead researcher Caroline Piole-Gorayeb remarked, science isn't about wishing for a particular answer, but about revealing what's real. In this case, reality has told us that TRAPPIST-1d is not an Earth twin, but with that answer comes a sharper focus for future investigations. With 3 planets, TRAPPIST-1b, 1c, and now 1d, showing no sign of thick atmospheres, attention turns to the system's outer worlds. TRAPPIST-1e, 1f, 1g, and 1h orbit farther from the red dwarf, potentially shielded from its most intense radiation. These planets, especially 1e, are now at the forefront of the search. If any of them still possess substantial atmospheres, Webb's instruments may be able to detect them, though the challenge will only increase with distance and the cooler environments these planets inhabit. To meet this challenge, astronomers are expanding their toolkit. While transmission spectroscopy has brought us this far, Webb's team is preparing to deploy the secondary eclipse technique, which observes the moment when a planet slips behind its star, allowing scientists to isolate the planet's own faint glow. This method helps sidestep the issue of stellar interference and could be key to revealing the atmospheric makeup of these more distant worlds. The broader implications stretch far beyond the TRAPPIST-1 system. Red dwarfs are the most common stars in our galaxy, and if planets can't hold on to atmospheres in these environments, it may reshape our understanding of where life could potentially emerge. But the search is far from over. Each new data point, each refined method, brings us closer to answering one of humanity's oldest questions. Are we alone? And let's not forget the astonishing technical achievement this represents. For the first time, astronomers have reached a level of precision where the existence or absence of an Earth-like atmosphere on a rocky exoplanet can be determined. Just a decade ago, this was the stuff of science fiction. Now it's reality. The instruments we've built, the methods we've developed, and the collaborative efforts of scientists around the world are opening doors that were once firmly shut. As we look forward, the Webb Space Telescope will continue to scan the skies, targeting not just TRAPPIST-1, but dozens of other promising exoplanet systems. Each observation, whether it yields a positive detection or another null result, adds a piece to the grand puzzle of the universe. The search for other Earths is a journey defined by patience, ingenuity, and a willingness to follow the evidence wherever it leads. For now, the TRAPPIST-1 system remains a tantalizing mystery, its inner worlds seemingly barren, its outer planets still holding their secrets. But with every new observation, we sharpen our tools, refine our questions, and edge closer to the day when we might finally glimpse a distant world with air, water, and perhaps even the conditions for life. Thank you for joining us on this voyage through the cosmos. If you enjoyed exploring the frontiers of exoplanet discovery with us, make sure to like this video and subscribe for more content like this. The universe is vast, and our adventure has only just begun.